So now that we have a feel for the basics of how a quadratic equation might behave when we swap its two roots back and forth, we saw an example where the two roots were -2 and +9, and those numbers were sufficiently different that when I switched them around, there are polynomials that they used to satisfy in this order that they no longer satisfy in that order. So -2 and 9, quite different. But then we saw an example of another polynomial, t squared plus 4, and its roots, plus and minus the square root of -4, they were so similar in view of the reals that if I switch them around, any polynomial that's satisfied in one order is also satisfied in the other order. So when I swap those two roots, nobody notices. The entire dining room is fooled when we trade out their gourmet coffee for instant coffee. So there's something different about those two polynomials because of that invariance under a switch of their roots. So we want to look and put that idea into the context of modern group theory. So we're taking a very modern viewpoint on what was done without our modern tool work by Évariste Galois. So let's see what Galois' guiding principle is and look at a couple more examples that help to illustrate how it works. The guiding principle behind Galois theory is that if we know which root interchanges matter to a polynomial, in other words, which two coffees can I get away with switching and nobody notices, then those interchanges are going to tell us something about the nature of those roots. And ideally, maybe it'll even tell us a process by which we can find those roots. So which root interchanges matter? Which coffees can I switch and nobody will notice? And which coffees, when I switch them, will people actually notice? Will polynomials that used to be satisfied no longer be satisfied? So you can fool some polynomials all the time, and you can fool all polynomials some of the time. But knowing which ones you can fool all of the time, and which root interchanges will leave all polynomials satisfied by those roots satisfied, knowing those interchanges will help us to understand something about this polynomial. So the definition that we make is that because these interchanges of roots are just permutation operations, they look just like elements of a symmetric group, then when we equip them with the operation of composition, we get a group, and that group is called the Galois group of your polynomial. So it consists of the group of those permutations of the roots of that polynomial which are irrelevant. So those permutations that exchange the roots that are similar enough. We have a notation for this. We say gal q of f. It's the Galois group of the polynomial f, thought of as having coefficients in the rational numbers. And of course, if we change rational for real or complex or integer or whatever, then we'll put a different symbol down there. And this is going to be the algebraic object, the group, that we attach to a polynomial that hopefully, if we understand the properties of that group, it tells us something about the roots of that polynomial. And here's an important observation. Because each one of these root interchanges is just a permutation, and according to the fundamental theorem of algebra, an nth degree polynomial will have n roots. Some of them might be the same as one another, but it has n if we count them with multiplicity. Then what that means is that this Galois group, because all it's doing is it's choosing some permutations of those roots that are irrelevant, some permutations that no polynomial that they satisfy will notice, that this Galois group is just a subgroup of the group of permutations on n symbols. So it's a subgroup of Sn, the symmetric group on n symbols. Again, all we're doing is we're choosing ways of permuting the roots of our polynomial. But we might not get away with every permutation. Some permutations will be noticed, and some might not. If I interchange two roots that are very similar, then polynomials will not notice, and that will be an element of our Galois group. But if I try to interchange two roots that are very different from one another, then chances are something's going to break. Some diner is going to notice, they're going to take exception to it, they're going to wonder why they're paying $6 for a cup of instant coffee, and they're going to walk out. And we won't choose that permutation to be part of our Galois group. So what this does actually is it sets up an entire spectrum of possibilities for what that Galois group can be. At one end, the Galois group could be trivial. This is going to be the case if no non-trivial permutation is irrelevant. In other words, if there's no permutation of the roots of our polynomial that we can do without falsifying some polynomial that they satisfy. This would be the case if all of our roots are so different that I can't get away with transposing any pair of them without breaking some equation that they used to satisfy. At the other end of the spectrum, our Galois group could be all of the symmetric group Sn. This is going to be the case if any permutation that we do of the roots is not going to falsify any polynomial equation that they satisfy. In other words, no one is going to tell the difference if we do any permutation to the roots. So at this far right end of the spectrum are going to be the polynomials whose roots are all very, very similar one to another over the rationals. And at the left end of the spectrum is the opposite case, where all of the roots are very, very different one from another in view of the rationals. But of course, we could have situations where the Galois group is anything in between. So where the Galois group of a polynomial falls on this spectrum gives us a clue as to sort of how many collections of very similar roots exist for this polynomial. If we can figure out a way to find this group without having to solve the polynomial and know what the roots are, then we've really done something deep and special. And that's what Galois was justifiably very proud of having done in the days and weeks before his death in 1832. So let's illustrate this with our concrete examples again, looking back at the polynomials that we saw in the previous video. So t squared minus 7t minus 18 on the left, t squared plus 4 on the right, and we can see their roots right here. So looking at the polynomial on the left, negative 2 and positive 9. We saw in the previous video that there is a relatively simple, in fact first degree, polynomial equation over the integers, 9 alpha plus 2 beta equals 0, which is satisfied by alpha and beta in this order, but only in this order. If we traded alpha with beta and got 9 beta plus 2 alpha equals 0, that equation was no longer true. So of the permutations that we could do to these two roots, and the possibilities are the trivial permutation and the interchange of alpha with beta, so swapping the gourmet and the instant coffee, only the trivial permutation could we get away with without falsifying something, because this particular polynomial, 9 alpha plus 2 beta equals 0, is satisfied in the first order but not in the second order. So we get rid of that interchange of alpha and beta because it doesn't leave this polynomial equation invariant. And so the Galois group of this polynomial consists only of that trivial permutation. The only thing we can do without raising any eyebrows is serve the gourmet coffee to the people that paid for gourmet coffee and serve the instant coffee to the people that paid for instant coffee. We can't get away with switching them. So the Galois group of this polynomial is just the trivial group. It consists only of that identity permutation. On the other hand, we have the Galois group of t squared plus 4. This was the polynomial whose solutions, plus and minus square root of negative 4, we said were very similar one to another in view of the rationals. So what does this mean? What this means is if I have any polynomial equation at all with rational coefficients that's satisfied by alpha and beta in that order, then it will also be satisfied by alpha and beta in the opposite order. So if f of alpha beta is 0, then f of beta alpha will also be 0. This is something we would have to prove, of course, but at least it seems kind of plausible, because from the point of view of the rationals, the square root of negative 4 is a completely alien number to the rationals. And so if I swap the positive version with the negative version, no one's going to notice. And so the entire dining room of diners won't notice if I serve people who ordered instant coffee, gourmet coffee, or vice versa. So no one cares. And so both the identity permutation and the transposition of alpha and beta will leave these equations invariant. So we say that the Galois group has both of those elements in it. So both the identity and the transposition permutation. So the Galois group of this polynomial G is isomorphic to S2, the symmetric group on two symbols, which incidentally is the same thing as Z mod 2 up to isomorphism. So the Galois group here is detecting a difference, an important difference between the solutions of these two polynomial equations. On the one hand, on the left, we had the two very different solutions to this polynomial equation, and because they're so different, we can't swap them out for one another and expect nobody to notice. So the Galois group is trivial. On the right-hand side, on the other hand, those two solutions are very similar one to another in view of the rationals. They're plus and minus square root of negative 4, which is not even close to being a part of the rational number system. So no one will notice if we switch those two out. No polynomial cares that is satisfied by alpha and beta. So the Galois group of that polynomial is the entire symmetric group on two symbols. Let's look at a higher order example just to make sure that we've understood what's going on here. So here's another polynomial, t to the fourth minus t squared minus 2. Just by a process of factoring this, and then using the zero factor property, yet again, we find out that here are its roots, alpha, beta, gamma, delta, the square roots of 2, and minus square root of 2, and then this plus and minus the square root of negative 1. Let's take a look at the first pair of roots, alpha and beta, that look awfully similar to one another, plus minus radical 2. If those satisfy a polynomial equation over the rational numbers, because alpha and beta are not themselves rational, if we want them to satisfy an equation over the rationals, probably what we're going to have to do is square them. Right? If I square alpha, I'm going to get 2. If I square beta, I'm going to get 2. So squaring alpha and beta make them into rational numbers. And so if I want them to satisfy some equation over the rationals, then I probably have to end up squaring them at some point. But the key observation is that once I've squared this alpha and this beta, I can't tell the difference between them anymore. Because alpha squared is 2, and beta squared is also 2. So in order to get alpha and beta to satisfy a polynomial equation with rational coefficients, I'm going to have to square them. But once I've squared them, I've lost the ability to tell the difference between the two. I've lost my taste for instant coffee and gourmet coffee, and I can't tell the difference between them. So in other words, polynomials over the rational numbers are not going to see a difference between alpha and beta. They're going to be the diners in the room that can't tell the difference between the two kinds of coffee. So here are the permutations that so far we know we can get away with. We can always get away with the identity permutation, but because alpha and beta both are identical after we've squared them, we can also get away with transposing one of them with the other. That's the permutation 1, 2, if we order these roots 1, 2, 3, 4. Then the same thing is also true of gamma and delta, this plus and minus the square root of minus 1. If they're going to satisfy some equation over the rationals, then we're going to have to square them. But as soon as I square them, because both of their squares are equal to -1, I can't tell them apart anymore. So likewise, the transposition of the third and the fourth roots of p is also a transposition we can get away with. But if I can get away with transposing alpha and beta and transposing gamma and delta, then I can get away with doing both. So the transposition 1, 2 composed with 3, 4 is also something I can get away with. So here's 4 permutations that I know I can do to any polynomial equation satisfied by alpha, beta, gamma, and delta over the rational numbers. But of course, there are some polynomials over the rationals that if I apply a permutation that's not in this class that we've listed over here, some polynomial will break if I try a different permutation. So here's a polynomial satisfied by these roots. Alpha squared minus 2 is equal to 0. And now let's suppose I try the permutation 1, 3, which is going to have the effect of swapping alpha with gamma, so square root of 2 with square root of -1. We get the equation gamma squared minus 2 equals 0. Well, the first equation is satisfied, but the second equation, gamma is the square root of -1, is not satisfied. So the transposition 1, 3, somebody will notice, namely the polynomial alpha squared minus 2 is going to notice when I swap 1 with 3. So 1, 3 is not going to be an element of our Galois group. And likewise, any other permutation in the symmetric group on 4 symbols is going to do something that some polynomial is going to notice. So the only swaps we can get away with are swapping the similar roots alpha and beta and the similar roots gamma and delta. That gives us these 4 possibilities. And this group is isomorphic to Z2 cross Z2, or the Klein 4 group. Why? Because every one of these permutations is a product of 2 cycles and therefore has order 2. So every element in this group has order 2, except for the identity, of course, which has order 1. So the Galois group of this polynomial is isomorphic to the Klein 4 group. Now here's Galois' dream, la rêve du Galois. The dream, again, is that this group can somehow tell us how to solve a polynomial equation. It's going to tell us how those roots were found. And the basic sketch of the idea is that starting from the original polynomial t to the 4th minus t squared plus 2, and starting from the Galois group, which in this case is the Klein 4 group, our process was we could factor this polynomial into a product of 2 factors, and that somehow, in the Galois theory, that's going to correspond to taking a subgroup of our original Galois group, the Klein 4 group. So maybe this particular factorization is going to look in group language like we're taking the subgroup Z mod 2. But then each one of those factors can be factored, and when I factor each one of those factors, that's going to correspond in group lingo to taking a subgroup of that Z mod 2. But since we have everything now completely factored, maybe at that point we've gotten all the way down to the trivial group. So the thread that we're going to pull on is that this process of how we solved this polynomial equation to find its roots, this process looks an awful lot like the process of descending from the Galois group down to the trivial group through a series of subgroups, which may or may not be normal subgroups. But if they are normal subgroups, and if their quotients are abelian groups, then this is going to have something to do with solvability. And that's the thread that if we pull on it long enough, and it's going to take us a couple of months and a half probably to do, but if we can pull on that thread long enough, it does unravel to show us why solvable groups have something to do with the solvability of certain polynomial equations. That's Galois' dream, and it's one that we're going to spend the rest of the semester trying to realize.